as Calvin said, my name's Gene. I'm the chief engineer for Astroscale Holdings, based in Tokyo, Japan, which is where I'm coming from for this presentation. As the chief engineer, I oversee all the technical management and execution of our programs and oversee the engineering team at Astroscale globally. So what I was going to do today was just give you a little introduction to space sustainability and why this is so important. And then I'll talk a little bit about my company, Astroscale. I'm not sure if many of you have heard of what we do. We are fairly new, and it's fairly new industry also, as far as space sustainability and in-orbit operations. And then I added a few extra slides about a mission that we have called ADRAS-J because we just launched this mission on a Rocket Labs launch a week ago. And so I'll give you a little update and some insight into how the mission's going. And this is something that we're really excited about, and I want to share with everybody. So to get going on the topic of space sustainability, so here's sort of a dramatic way of showing you why this is important. So here's an image of all the human objects in space in September of 1957, which is zero before Sputnik. And then here is an illustration of all the objects in orbit now. And you could see why this is a concern. In fact, here's another illustration, an animated one. This focuses on the LEO satellites, but you could kind of get the point here visually, why we need to start paying attention to space sustainability. There's a lot of objects in space. So, there's various statistics you can look up. The point is there's a lot of orbital debris in space, and there's sort of two regimes in LEO and GEO, but they both have a lot of objects there. One reference point is there's up to 36,000 objects of debris that are 10 centimeters or greater. There's almost 3,000 satellites that are no longer operational or decommissioned, and almost 2,000 upper stage rockets still orbiting the Earth after they completed their mission. And then, yeah, again, you can look up all different kinds of specs and information about this, but there's another thing that's important about this. It's not just the number of objects, but what makes this problem challenging is that, we're due to orbital dynamics, these objects or this debris is traveling at, depending on the orbit that you're in low Earth orbit, as fast as 28,000 kilometers per hour. It's a slower velocity at GEO, but the point is these things are going really fast. And because they're going fast, they have a lot of energy. So even the smallest little particle, that's just a few millimeters, going at this velocity has a lot of energy. And if it collides with a satellite or even, astronauts in space, it's a huge risk. The other reason this is a concern is collisions, when they do occur, can create more debris. And then there could be this cascading effect, which is also referred to as the Kessler syndrome, if you haven't heard that. But this was Donald Kessler, proposed this concern back in the late 70s, called the Kessler syndrome, where you could have enough debris that when one object collides with another, it creates more debris, and then there is an escalating effect and a cascading effect that additional debris could create more debris. So these are reasons why this is a difficult problem and a concern. Okay? But all this is in space. So, why does it matter to us? Well, there's two key things as far as impacting us in daily lives. So, one is we this day and age with technology, and a lot of people take for granted that we rely on satellites to live our daily lives. So things like even the weather forecast, uh, communications, disaster management. Uh, One thing that we all rely on our phones is GPS. GPS uses satellites to be able to track your locations, and a lot of other applications. And so we live in a day and age where we directly or indirectly rely on satellites to for everyday lives. And so we need to look and address this issue. There's a second issue, though, that you may not be aware of, and this is for satellite operators. So, these companies like us and others that launch and operate satellites, what you may not know is that if you have a satellite in orbit, you have to operate it and keep it safe. And what's happening is these satellite operators are getting more and more conjunction alerts, which are alerts of potential collision. And so this plot here shows the monthly Leo conjunctions that are within 1 kilometers has astronomically increased in the last 3 or 4 years. Now, uh, a lot of that has to do with the increase in the Leo constellations that are being launched and the numbers. You could see, um, since 2021, there's about 4,300 operational satellites in orbit, but the projection is up into 2030, there could be as many as 46,000 satellites. And then we can't forget that we have people in space. So right now, we have the ISS and the space station. There's people on board there, but there are projections and proposals for commercial space stations, and there could be more people and more opportunities for people to be in space. And so these increases in the satellites in orbit, they increase the number of conjunction alerts. And what happens now today, if you're a satellite operator, is if you're flying around your satellites in orbit, you'll get an alert that says, oh, there's a potential for a collision with an object that's coming up in like 1 or 2 days. They could forecast it out ahead of time. And so you have to monitor that. And then a lot of times, or sometimes, depending on the case, you may have to maneuver the satellite uh, away to reduce the probability of collision. And that affects resources, fuel, and a lot of operations. And so these conjunction alerts are making it more difficult to fly and operate a satellite. So these are all reasons why space sustainability is something that we need to start looking at and addressing in our industry. So now let me tell you a little bit about my company, Astroscale. So we're looking to try to address this issue. And one thing that's interesting is why we were named Astroscale. So our CEO always tells the story that he had always thought where the name came from is Astro is kind of um, implies space, but scale is referring to the balance of development and consideration of the environment. And that's sort of a little insight and some history into why our CEO and our founder chose the name Astroscale. And one of the things that he always talks about is, we're not against development of space or putting more satellites up. We want to foster the space industry, but his point is that we have to do it in a balanced way, in a smart way, and that's why he chose the name Astroscale. So a little bit of statistics on our company. We are a global company. We were founded in 2013. We have offices all around the world. The headquarters is in Tokyo, which is where I'm based. But we do have two offices in the US, in Denver and in DC. And we have offices in Europe. And we just recently announced an office in France, in Toulouse, France, this year, last year in 2023. We have about 550 employees worldwide, which has grown a lot. When I started, I think there were 80 people. So we're growing very fast. And we've been fairly successful in raising capital. Up to now, we've raised about $383 million in capital. So we're a growing company. And what I want to highlight is that we're international too, because one of the things that our founder always and CEO always talks about is that solving this problem it's an international uh, issue, so it needs to be addressed globally. So here's our vision and mission. Our vision is to have a safe and sustainable development of space for the benefit of future generations. And our mission is to develop innovative technologies, advance the business case, and inform international policies that reduce orbital debris and support long-term sustainable use of space. And so this is our vision and mission as a company. So how do we do that? One of the things about our approach to space sustainability is we look at the problem holistically, and we want to try to foster what we call a circular economy, a sustainable ecosystem. And to do that, we address things from various different angles. So, on the left side is risk and mitigation. So we need to be safe, have good practices, and it's not just technology, but we also are involved in and supporting regulations and policies that has to complement technologies, and then have people accountable and make sure there's global coordination and communication within our industry. But the whole idea of a circular economy is it's not just trying to put rules in place or restricting development, but we also want to work with the manufacturers, work with the satellite operators and people in the industry, and we want to show them that there's a benefit. There's a long-term benefit in what the return on investment is. You want to have various strategic options for customers, and I'll talk about how we do that in all the different services that we provide. And we want to try to accelerate this mentality of finding ways to develop space in a smart way that's also economical and good for everybody in the business. So, there's some aspect of sort of doing things to benefit yourself in the long run. And then you could see on the right here sort of all the different aspects of sort of a circular economy that we want to push and foster. So there's the reuse, repair, recycle, regenerate, remove, and reduce. And those are all sort of aspects of space sustainability and having a circular economy that we want to see. So how do we do that? Well, one of the ways we do it is for developing technologies for on-orbit servicing. And this chart here kind of is an interesting perspective. Is on the top chart, if you look at industries here on Earth, the logistics energy, the energy communications, other industries, it can start with R&D. There's technology that gets developed. You develop a product or a service, and then you go into operations. So you have customers, you do operations, and then in that industry, it always comes with the post-sale servicing and support. So if something breaks down, you repair it, you do the maintenance, and then you do final disposal. And that aspect is how you have a circular economy and a sustainable industry. Well, if you compare that to space, you could see that we've never had that aspect. So in space, there was a lot of technology development. You launch and we do satellite services, but we never really addressed that last aspect of it. And so this is a good way to illustrate what we mean by space sustainability in a circular economy, is we need to address that last aspect of our industry to make it sustainable. So how do we do that? So at Astroscale, we have various types of technologies and on-orbit servicing to try to address this industry. And pictured here are sort of the 5 key types of services that we are working on along with the projects. And these are all different services for various types of customers and services in all different kinds of orbits. So on the left, we have life extension services, and we have a program called LexCP. It's in GEO. And the idea here is to rendezvous with the GEO satellite and then extend its life. So here it's the reuse approach. Instead of throwing the satellite away. And a lot of times, the life limiting factor for a GEO satellite is fuel. And then the hardware or the communication payload works fine. But when you run out of fuel, you have to deorbit or put the satellite in a graveyard orbit. So we have a mission or a concept called life extension, where we have a satellite that will rendezvous with a GEO satellite and attach to it and then extend its life. Another aspect is space situational awareness, or what we call ISSA. So this is a fairly new area, and it's basically taking a satellite and rendezvousing and doing inspection of satellites, and also it involves sort of tracking and and observing all the debris in the satellites in orbit. So, one of the issues in in space sustainability is getting good, accurate knowledge of where all the satellites are in orbit. And so ISSA is an aspect of this, which is getting accurate and quality information about where the satellites are, what condition they're in, and that can help with knowledge and information to manage your satellite fleet. And there's where we have a mission which I'll talk about in a minute, which we just launched called ADRAS-J. The next one is what we call end of life services, or EOL. And also it has the same capability as orbit transfer. This is a concept where current constellation deployment operators, they deploy hundreds and thousands of satellites into their operating orbit. And those satellites, because they operate in a certain orbit, when they reach the end of life, you need to move deorbit or move the satellites out of your orbit. And if you don't, then you're basically potentially could be causing debris or risk of collision to your own satellite because you're in the same orbit. And one of the ideas is we have a concept called end of life services where we will go to these constellation operators and provide a service where we could rendezvous and capture and then deorbit any satellites that may be in their fleet and in their orbit to clear that orbit up so they could continue to operate. And that technology is also similar to orbit transfer, which is sort of moving satellites to different orbits and orbital planes. Uh, and on this type of service, we had a demonstration satellite called ELSA-D that we launched 2 years ago to demonstrate some of those technologies. And we have two other programs that we're working on that provide these kind of services. And then the fourth one, active debris removal, which we refer to as ADR. So this is a type of service remission, which is to go after defunct or old objects. So these are objects that are already in orbit, and then to try to rendezvous and capture them and then deorbit them. This particular type of service is very challenging because a lot of those objects are been in orbit for 10 years, 15 years, so we don't know what condition they're in. There's no controllability, so they could be rotating. And so the capture process is very different. But it's basically the concept of cleaning up old debris that's already existing. And that's what we call ADR. And then the last one is services, refueling, maintenance. If you can rendezvous with the satellite and then you can make it refuelable. Again, a lot of times with satellites, fuel is the one of the main limiting factors in ending the life of a satellite. So just like, in your car, when you drive and you run out of gas in your tank, you don't throw the car away, you fill it up again and you can continue using it. The second most life-limiting factor is the batteries. So just like your iPhone, if you have an old iPhone that's 5 years, 8 years old, it starts to not hold a charge. And then makes it so it's not as usable. So if you could replace the battery or upgrade it, then you could continue to use the satellite without having to throw it away. So refueling and servicing is a new technology. It is still being developed, but we see that as the future to again help address this space sustainability. So all of these things are services that are either new, that require new technologies, but there's two things. One is the underlining sort of mentality of how we deploy satellites needs to change so that they could become serviceable. The second thing, at least for us at Astroscale, is these are all different types of services with various clients and various orbits, but there is an underlying technology that's needed to address this, which is what we call RPO technologies, rendezvous proximity operations. So one thing that's common for it to be able to establish this industry in this market and to be able to sort of change this mentality is we need the ability to do RPO technologies. And so what is RPO? So there's various elements to be able to rendezvous with an object. It's a little more challenging than a rendezvous with like the space station that they do now because there is people in the loop and there's two-way communications. The additional challenge that we have in rendezvousing with other satellites and objects are the box number one there is knowledge of the object. So if the object is no longer communicating, it doesn't have GPS, there's no way to communicate with it, then having accurate orbit knowledge to be able to rendezvous with is key. And that's part of one of the services that I showed earlier, ISSA, which is trying to track and get knowledge of the location of objects. Then step number 2 is what we call absolute navigation, and that is rendezvousing with the satellite in orbit. And if any of you guys have taken your orbit dynamics classes, you know that rendezvousing and changing orbits, especially inclination and RAN, or the right ascension of ascending node, is not easy. It consumes fuel, and there's a lot of uh, orbit maneuver planning that's required to be able to approach an object in space. Then once you get close, then we go into what we call relative navigation. And what that is that once you get close enough, we have a sensor suite on our satellite that can detect the client or the object close by, and then we rely on that sensor information for the servicer satellite to navigate to get to the close approach to do the inspection or the capture of a client. And so that is another technology that we have developed in-house to be able to do the relative navigation, and that is done by various sensors and various algorithms to be able to do that approach. And then once you get close to the client, there is the controllability around the client to be able to move around, inspect it. And then one of the biggest challenges of RPO is if the object is uncontrolled and it's tumbling, then as you approach it, we want to be very careful not to collide with it or damage it and then potentially create more debris. Then we're going to make things worse than what we're trying to solve. So safely approaching and being able to align with the object is another aspect of RPO that's very challenging. But then once you could do that, then step 5 is the actual capture and stabilization. And that technology requires robotics and various capture technologies. And then finally is the transfer, is to move the object if needed to either a different orbit or to deorbit the object. So these are sort of key technology areas for what we call RPO technologies. And these are technologies that Astroscale is working on and is fundamental in all the missions that I presented before. So this is sort of an illustration of what I just referred to before about which of those RPO technologies that we're developing in-house. So we do have the ability to do satellite assembly and test so that we could build our own satellites. Our satellites to do these missions are slightly different and unique from any regular satellite. And so there isn't any off-the-shelf satellite that could do these missions that we found. So we've consciously decided to be able to integrate and build these satellites in-house. Robotic technology, as you saw from our previous chart, the capture mechanisms is a key aspect of RPO. So that's a technology that we are working and developing. Software algorithms, that is so key in rendezvous, is not just the spacecraft and hardware, but all the algorithms to be able to process the imagery, to be able to maneuver the satellite, and then to do that semi-autonomously and to do it safely is a key technology that we're developing at Astroscale. And then finally, one thing that people take for granted or may not think about is the operations of the satellite. So these types of servicings require a different approach to operations because when you get close to a client, um, especially in LEO, low Earth orbit, there's you can't get always have continuous contact and coverage. So you have to make sure that once you get close to the client, that when the satellite is out of view, it's safe and there's some semi-autonomous operations. Safety is a huge thing that's very important to us because um, again, we don't want to risk creating more debris by having a collision or an accident when we're trying to rendezvous with an object. So operations is key to make sure that we approach the satellite safely. So here at Astroscale, we've launched two satellites. Uh, One of them is called ELSA-D back in March of 2021. That is a demonstration satellite of our magnetic capture technology. And actually, I'd be happy to answer questions about that later. But I wanted to focus actually on the second satellite that we launched, ADRAS-J, because that mission was launched, oops, sorry, just last week. And so what I want to do now is kind of go into a little bit about the ADRAS-J mission, and then I'll give you a little insight and some highlights on how that mission is currently going in orbit right now. So here's an image of the satellite, some details. It's a small, relatively small satellite. It's about 150 kilograms, fully fueled. You can see the dimensions there. They're in meters, but it's about the size of a little refrigerator. It does have 12 thrusters that use green propellant. We specifically chose that to try to be, again, sustainable and environmentally friendly. It generates about 500 watts of peak power. And this mission is going to approach an existing H2A upper stage um, object. That object is about 3 tons. It was an object that was launched in 2009 uh, for the GOSAT mission. It's currently at around 600 kilometers altitude at 98 degrees inclination. And that's the object that we're going to rendezvous with. So what is the ADRAS-J project? Um, the project is to try to demonstrate, it's a demonstration mission. This has never been done before commercially, to demonstrate the technologies for on-orbit debris removal, or what we call ADR. It's a unique project. It's a public-private partnership with JAXA, which is the Japanese space agency. They have a program called CRD2, which stands for the Commercial Removal of Debris Demonstration Program. Um, they they have divided this program into two phases, phase one and phase two. So so the object of CRD2 is it's a technology demonstration to be able to show how to remove large debris. And what's interesting is the way they modeled this program is they are a service-oriented contract. So they provided funding to Astroscale to provide a service to demonstrate these technologies. It's not a traditional procurement of a spacecraft that JAXA is used to before. Here they want to provide a service and then try to foster a potential for commercial service in the future. Uh, the program consists of two phases. So the ADRAS-J satellite that was launched is only for phase one. And we were selected in February of 2020. And phase one is a demonstration to only rendezvous with the upper stage, get up really close and do various technology demonstrations, but not actually grasp and capture the object. So the purpose of phase one is to rendezvous and do close approach operations. Phase two is to actually go back to the same object once we have the information and proven the technologies, and then to actually capture and then to deorbit that object. And so the status of phase two is that Astroscale has been down selected as one of two companies back in August. And JAXA is currently evaluating the proposals from those two companies to make a decision. We hope to expect this year on who's going to go forward with the phase two portion of the mission. But I want to talk about phase one, ADRAS-J. So yeah, as I mentioned, we had a successful launch just a little over a week ago. We partnered with Rocket Labs for this mission. And actually Rocket Labs was a good partner. And one of the unique things about this type of mission is because we have to rendezvous with the client in orbit, the ideal launch provider is a dedicated launch, because we have to go to the certain orbit that where the client is. In fact, for our launch, we had actually basically an instantaneous launch window of only a few seconds. It's not exactly instantaneous, but our launch window was very tight. And fortunately, Rocket Labs delivered us right on target, right on time on the first try. And we had a successful launch. I was just mentioning that after it took about 60 minutes for the launch and separation. And within 10 minutes, we had a ground station pass that we weren't expecting anything, but our satellite booted up and phoned home right within 8 minutes of separation. And so right away, we started off on the right foot, and it was very exciting. So what I have here is a little 3-minute video that I want to show. It has a graphic illustration of the mission. And so I want to show that now, and then I'll talk a little bit about the details of the mission. So here's a little video. Okay, so here are the different phases of the mission that you saw in the video, and I just want to briefly talk about the challenges and what we're trying to do. So, obviously the first step is launching and getting in orbit and making sure that the satellite is safe, stable, and operating and checked out, that everything is working as designed. Um, then what we do is we go into a rendezvous phase. And this classical orbital dynamics um, maneuver. So we raise the orbit slowly to start getting close to the client. Um, and this is where one of the challenges I said earlier is that we know where we are because we have a GPS receiver on our satellite, but in this case, the client doesn't have a GPS receiver, so we have to rely on ground observations to know where the client is, and that ground observation is only accurate to a couple hundred meters or so. So there's still a lot of uncertainty. And so this first phase is to get close uh, uh, with just regular classical aerodynamics. And then we get to what we call proximity operations. And this is where the real key part of the technology of RPO comes into play, which is when we get into range of our sensors of our satellite that could detect the client. And we have various sensors on board that was mentioned in the video. We have a visual camera, we have an infrared camera, and then we do have a commercial LiDAR system. And those are three different types of sensors that are used for three different phases and different purposes. But the key is and the huge part of this demonstration is to show that we could transition to relative or proximity approach operations using these sensors. And based on the information that the satellite collects when it gets close, it uses that information to get close in, like you saw in the video. And then once we're able to demonstrate that, then we want to show that we have controllability and proximity operations. So the key requirements from JAXA is we need to have fixed point observations where we hold steady and see how the client is rotating, and we could get photos from a fixed point perspective. Then you could saw from the video is then we do a fly around to show that we have maneuverability. So we take the information that we collected and then we use our algorithms and control system to maneuver the satellite around 360 degrees of the satellite. Uh, and then the final part, which is the most exciting and the most challenging, is we are going to take the knowledge that we collected from that, know how the object is rotating, and then we're going to match the rotation rate and then get close up to the adapter ring, a certain side of the upper stage, because that is the method in then we are proposing for phase two to actually capture the upper stage. So this mission will prove the technologies to get very close, and we do everything up to what's needed to do the capture without actually doing the capture. So that is the plan for this mission. And then once we've shown that demonstration, collected all that data, the last phase is the departure and the deorbit of our satellite so that we don't create any more debris. So where we're at today, so it's only been a little over a week. I'm happy to report that the LEOP and the commissioning has been successful. In fact, we've been ahead of schedule, and the satellite is in good health and working as designed. And then we just announced that we started the rendezvous phase. So we've started to raise our satellite and we're on track to start approaching it. And then the key phases is the proximity approach and the proximity operations. And the time frame to complete those missions is on the order of 2 to 3 months. So it will take a little bit of time. And one of the reasons why it'll take a few months to complete those is it is new technology and a demonstration. So we want to be cautious and make sure that we prove things out and things are working as designed. But the other thing that I want to stress and highlight is we want to do it safely. And we want to approach the client safely because one of the things that was a mandate from JAXA and something that we are very believe strongly on Astroscale is to make sure that we don't risk creating any new debris and we design and architect technologies and approaches that can approach a client safely. So the key and the exciting parts of the mission will probably be 2 or 3 months away, and of course we'll make announcements as we go along. But hopefully, I could announce, or maybe I could come back and give you an update on how we succeeded. But this is um, a mission that we are very excited on, and it will prove out a lot of technologies needed for those services that I talked about.